Okay. Okay, so the goal then is to start with a manifesto that to declare why it would make any sense to care about internal infinity categories if one only cares about, let's say, synthetic topology. So let's go back to our something that I think a lot of people in this audience care about, namely synthetic algebraic topology. Which one can kind of summary can describe as trying to do topology, but not just in the classical math, but somewhere else, either in some homotopy type theory or some infinity topos. Right? And so I kind of summarized a collection of results that I like, such as computing the fundamental group of circle, or Blakers-Massey, or computing pi4s3, truncation, finiteness theorem, looking at stable homotopy theory and stabilizations, chromatic homotopy theory, and homotopy algebraic structures. So this is like a bunch of stuff that has happened roughly from the early 20th century up to 1960s. These are like some of the major developments. And a lot of them have already been generalized or either formalized or either improved upon. So the fundamental group the kind of computations go back to ideas by Brouwer. But I think like the official paper on this that I could find is by Hopf from like the 20s. And the first formalization I could find on this is this paper by Licata and Schumann. That is, I think, from 2013. So around 100 years later, the story starts. And then Blakers-Massey happens where by Blakers-Massey, so I don't write the names again. But the first paper they have is on 49, right? And they have a series of papers. But Blakers-Massey already as a theory applies in the hot book, right? So it's in the hot book already. So around 2013. A nice formalization, I think, in ACTA, I think in 2016. So it's a very meteoric rise, right? Like we almost immediately have some of the earliest results very quickly. Pi4s3, famous in all of the hot community is the Lunari number, right? So of course goes back to the work of Lunari. And I think 16 is the thesis, but then the formalization was quite recent. Thank you. Yes, this is here. Thank you. And of course, the original computation goes back to Freudenthal in the 30s. I think 37. So again, very meteoric quick rise. Truncations, the first paper I can find on truncations is by Postnikov. It's actually in Russian. I could not read it. But apparently Postnikov thought about this in the 50s. And then a bunch of other people, so like Kahn, for example, worked on this, and other people around the 60s and continues. But then on our side, so then there's a bunch of stuff that has been done on this. So for example, Egbert has this nice joint construction paper, which has a truncation. Of course, in some sense, the work by Rasekh, Spillers, and Schumann, or the RSS paper, has kind of stuff modalities, which, well, is related to this. And then there's this nice paper by Christensen, Opie, again, Rasekh, and Schumann, the course. Sorry? It is, yes, sorry, thank you. In 20, also talked about like localization and truncations. And so this is, again, like we can run just the time span of 2013 to 2020, we have like a lot of development happening very quickly. So, awesome. This is a great start. And of course, I mean, the point I want to make is that things don't go as smoothly from here on, right? So something slows down. So further Serre's finiteness theorem goes back to Serre himself in 53. Here, I don't know. I'm not aware of any kind of either result or counterexample or anything in this direction here that's complete. Yes? Yeah, can you speak louder, please?
I think this by and
which proves that it is always finite except for the G. So there's a weaker form of it. It doesn't prove that is.
read the for thematic camping.
We can discuss this, but okay. I'm not aware of this, but I'm totally willing to believe it. But like, on stabilization, there's a lot, so I cannot cite all of it, but like, of course, Nima introduced spectra. But then the main thing that I would care about is, for example, stuff like not just the definition of spectra, but a lot of the theory, right? So the calligraphy spectra, mapping spectra, the symmetric monoidal structure, and so on. And this, I don't know, goes into the 60s and 70s. A big figure on this is, for example, Adams. And here there's cool stuff in HoTT, but not all of it, as far as I know. So, for example, there's this nice thesis of Floris van Doorn. Okay, I mean, not tools. Okay, what is this right? For example, we just define spectra, but some of the story is still missing, right? So the more category theory spectra, I think, still needs work done. Chromatic homotopy theory, okay, that's like a very broad field. One important result I could mention here is the work of Adams in the 60s, who famously characterized the so-called J homomorphism, an image of a J homomorphism in the stable homotopy groups. This, I'm not aware. I'm happy to hear if it has been done in HoTT, that would be really cool. But okay, this one I was right. So that other one I was mistaken, but here, okay, there's not much. And finally, homotopy algebraic structures. So either like doing operats or, so this goes to May in 72, or Lavier theories, right? So I think in 63, due to Lavier, of course. And here again, I mean, there's of course lots of stuff on specific algebraic structures, but not at this level of generality, right? So like I cannot just do like an EN algebra yet in some like arbitrary setting. And so what we would like is, well, have exactly the same kind of either cool results that we have at this level, like this part already, but like at this like lower half. Slash, maybe this one's already done and just missed it. But at least this half, I would say, is like needs work to be done. And one could ask, okay, why is that the case in the first place? Like, why is it that this first half is kind of like done so nicely and so like has been so much development has been done, but in the second half not? And of course, the first simplistic answer is it's just harder. Like the math is harder and harder math is harder to formalize. That's like obvious. But I think there's also something else happening here, namely it's the influence of category theory, right? So as we kind of progress down here in this line, there's more and more category theory showing up. As a matter of fact, the first results here, there is actually no category theory at all. Like when Hopf was doing this kind of stuff, categories have not really been defined. But at the end, when we get to this endpoint, like really kind of operats and stuff, they kind of have category theory built into the construction, fundamental. And so what you would like to have then is some nice way to do category theory kind of internal to the setting that we would like to do. And I don't want to be like totally negative on this. Like a lot of stuff can be done without like explicitly doing category theory. Like so sometimes we can do category theory without categories. So let me mention this. Let me give you two examples of what I'm talking about. And my favorite example of this is sequential colimits. So if you leave the room and walk down to the street and then find someone, ask them, okay, what do you think is a sequential colimit? They're probably going to be very confused. But now if you know they are a geometer or like a geometry group theorist or something, and you ask them what is a sequential colimit, probably they're going to give you an answer like, oh, I have a category and I have this diagram. The sequential colimit is this like universal thing out of this diagram, blah, blah, blah. And so in other words, kind of people pre-assume some kind of notion of category to do sequential colimits. But turns out we don't really need to, right? And there's this nice, for example, there's work by, again, Rasekh on this, studied the joint construction. And there's also follow-up work by, let me not mispronounce the name this time, Sojakova, Van Doorn, and Rasekh, and who kind of work on sequential colimit in HoTT by just translating kind of, okay, what does it mean to have a sequential colimit, but you just explicitly kind of unwind it into your kind of set. And I also do similar stuff on this in like an infinity topos, also like using a universe. So kind of it's kind of like a, sequential colimits where you just have a notion of like composition and mapping objects enough to get things done. So yeah, again, here there's like, look, there's stuff by like 17, then what is it? 20, okay. And I guess this. Another kind of like nice example that I like is localizations. So by localizations, usually people think of, okay, it's some kind of a junction where the right adjoint is fully faithful or something, and then there's some other properties. But again, you kind of can unwind this to just focus on the, like, you have your universe, you want like some kind of like sub-universe with some kind of nice properties, and you want a reflective sub-universe. And this, of course, like has been studied very extensively in this like nice paper RSS. It also like now has been like follow-up work to kind of compare this at least to some of the external setting by Vergura. Yeah, so here again, also like, yeah, it's kind of nice to notice. So there's the very kind of now famous papers by ABFJ and Biedermann, Vincent Joyal, kind of secretly rely often on this understanding of localization as this kind of internal sub-universe without kind of making this very explicit in some places. So there's ways to kind of get around this in this setting of localization. However, a lot of cases this doesn't work, right? So doesn't always work. Right, so things that play a lot of an important role in modern topology are things like presentability, adjoint functor theorem, I don't know. Pick from a long list of very important classical categorical results that topologists use on a daily basis. Okay. So what we would like then is a more kind of structured approach to our categories that can kind of incorporate more advanced category theory into our machinery, so that we can use this to do the topology internally. Okay. So this is the end of my manifesto. So I hope at least one person is convinced that this is a valuable goal. Because if not, then I don't know. I can stop right here. Okay, so assuming that at least one person is convinced, let me now state a conjecture then that tries to exactly tackle this. And so I work in a setting of infinity categories because that's the only place where I would even know how to talk about internal infinity categories yet. But theoretically, there could be like type theory versions of this as soon as the type theorists figure out how to do internal infinity categories, which is like way beyond my pay grade. But I'm optimistic people will figure it out. So let E be locally Cartesian closed infinity category with universe U. And so I guess if you care about type theory, then you should think of this as some kind of like type theory with pi types, I don't know, sigma types, a univalent universe, and like path types and so on, right? So the kind of classical standard classical standard place where people do like type theory. So this should correspond roughly to this. Then, so number one, there exists a notion of internal infinity category in E, in E, and it comes with a category too. Number two, E itself can be internalized into itself so that we can study it as an internal infinity category using the internal language. E can be internalized to E infinity category, like the line below, such that, so why do we think of it as being its own internalization? More or less, its global sections should correspond to E, But of course, then if I do this, Russell will come and scold me. So there should be some like size issues, so, like this small or something, up to size issues. In particular, the internal infinity category cannot have the universe as an object, right? Because then that will be an issue. But ignoring that one thing, it's more or less this should be true. And then finally, this is also like the kind of cool result that you want to have here now is that this internal infinity category is co-complete, but internally, of course. And in fact, the co-completion of the terminal object. All right. So this is roughly what we know to be true for, I don't know, in classical settings. And so this should translate internally into a statement for the non-classical. Okay, so which one of these can be proved and which one of these we have no idea about? That's the point of this talk to find out. Before I discuss this, let me mention some implications. And I have a long list, but I will not say all of them because it gets boring. But I mention like two. First of all, it would give you a very formal way to kind of do exactly things like sequential columns, right? Or like geometric realization, right? Because in particular, if you co-complete, then for example, like if you take n to be like an NNO, then it would follow that now you have a co-limit functor here. For example, right? So it's quite immediately. You have to like do this by hand. Similarly, so for example, assuming that you can show that tau NE is co-complete, the n truncation, the subcategory of n truncated objects, here E, then you get a truncation functor from which is the unique functor here, the unique functor that preserves the terminal object. So this is usually not that easy to construct, right? Like if you're just working in constructive math, but like it would just come out of this like this. Kind of like an elegant thing to do. One reason I really care about this, and this comes back to this last item here, is so I would really like to study like this kind of algebraic structures in this setting. This is really hard because like homotopy invariant algebra is really hard. Ask the homotopy. They will tell you. And so assuming that we could define some kind of internal category of algebras, some sort of E infinity category of algebras, then one thing I would very much like to have is like this kind of free construction. Right? This is like if you go back to the non-homotopical setting, so elementary topos theory, you open like Johnston's book or something, right? These sketches. You will find like an explicit description that if you have some kind of like monoids or something like this, you have like a free monoid associated to every object. But there, kind of the construction goes by hand because the structure of a monoid is very, very kind of limited. Right? So what is a monoid? You have an object, you have one multiplication map, associativity, you're done. In this setting, it won't be that easy, right? So your object would be like A infinity in some sense, presumably, or En or something, and then you have like infinitely many coherences. So it'll be very hard to construct this by hand. But here, then, it would just follow by exactly just knowing where to map the one. So you need only know the free monoid generated by one, for example, free algebra of one, and then you would have your whole function. So this is the kind of like things I'm after. So that kind of motivated me to like set up this theory. All right, so yeah, so these are some of the implications. But that's just some examples. I mean, this is stuff I care about. I'm pretty sure if you think about stuff, you can come up with other applications. having kind of these three implications very nice. Okay, so now that we have established this is an interesting thing to study, how can we do it? And I guess the first question one should ask is, where would such an internal infinity category even come from? So that's a question that one would to answer. And well, the next title as that tries to address this is a so-called, let me write it like this: category theory versus type theory internally. All right. So if I ask this room, I want a category, where should I get one? Then I think the reasonable answer that you would get is to get it from a type, right? If you have a type theory, then you can usually construct a category out of it. And usually if there's some structure on a type theory, there's some structure on a category. That's a very reasonable answer, right? So there's this rule, like, and there's of course a very precise statement here, right? Using comprehension categories, categories of families, and so on. But just very broadly, one can think of like, yes, if I have some kind of like type theory, and then I can translate from a type theory to a category where like my types are kind of supposed to be like objects, and my terms are kind of supposed to be like the morphisms or something. And then there's like these nice constructors here. And what the constructor should be is something like universal properties. Here. And so if I want to construct an internal category, it would be nice to have something that looks like an internal type theory. So that's so what would be an internal type theory? Then it would be some object which has some kind of constructors on it. This is I'm not studying a mathematical result, just a heuristic of where like internal categories could be. Let me try to like give you at least an example. Like I'm not going to like state a formal theory here, but as an example at least. So inside category theory, for example. Inside category theory, we have an object called a sub-object classifier, or we can have an object called a sub-object classifier. And in the standard way, the sub-object classifier is described as a kind of object omega with some universal property. So that the sub-objects of a object is naturally bijective to maps into this. And then we have various constructors on it, right? So for example, we can take the meet of two sub-objects, which is kind of like a morphism from like this. So we have an object and we have like a constructor on it. Cool. And so this is kind of what I would say the type theory-like description. But there's also, we can like actually endow omega with something like a more of category-like structure. Namely, omega is a Heyting algebra. I'm using the word algebra, but the Heyting algebra is really a zero in a more or less precise sense. And then these properties here will transfer to various properties of the category, right? So you have products, you have coproducts, you have some nice compatibility, you have Cartesian closure, and so on. Another example is then in infinity category theory. We have object classifiers. So there's like someone a U, and then there's an equivalence between, I didn't give my category any names, but let's say it's still E. And like this is equivalent to maps into U up to size issues. Let's ignore that. And if you wanted to play the same game, then you would expect that we can endow U with some kind of infinity category structure. So question one. Let me now mention here, so I cannot like really do much here, but like presumably in a type theory setting. So if you take the universe U itself, then of course the universe U comes with a structure, but I don't really know what to do here because again, I don't know what the internal infinity category in some type theory would mean, but if one could make meaning of this, then I would like expect some similar kind of analogy to hold. So yeah, so the kind of conjecture one makes here is then that given if I have my infinity category, my universe, my universe should be able to use the internal structure of the universe and the constructors it has to lift it to some kind of like infinity category. That's now the aim. That's what I'm aiming for. All right. So can I make this precise? So that's the next title. Constructing internal infinity categories. And so in order to do that, first of all, I have to like say what the internal infinity category is at all. And there's like a fairly standard definition now in the literature. So I will do like a quick review of this. And before I move on, I should like stop for a second and ask the questions.
Sorry, when you say the factor reconstruction of omega, I mean, maybe it's equivalent of another thing, I would say H4.
Yeah, well, yes, but like, exactly. Yeah. I don't see in the back, so if the questions you really have to talk, but if not, okay, so what is an internal infinity category? So definition, let's see B as before, oh, E. And is a simplicial object W from delta up to E that satisfies, here I'm going to be as vague as possible, some finite limit conditions. So the backstory of this is that essentially Charles Rasekh wrote a paper where you kind of like, you start with like, think of the naive classical nerve and you kind of generalize it appropriately to high category setting by recognizing what conditions you want. That's the gist. And for that reason, these are called, sorry? Yeah, I was to say. So that's why these are also called complete Siegel objects. So you need the completeness and the Siegel both. They're also sometimes called Rasekh objects. And for the type theory people in the audience, this is also like the basis of these notions of Rasekh type.
The completeness of the universe.
Yeah, exactly. Yeah. So this is like, yeah, there are various ways of phrasing this, but it's all essentially the same. You have like some visual object, you want the Siegel condition, the composition, and the univalence / completeness, which to make it be good. So that's the notion of infinity category can work with. All right. So now can we like now lift our U, the universe, to a simplicial object? And fortunately, the answer is yes. So let E be as before. Then there exists an internal infinity category E such that, I mean, essentially has the properties you think it has. So for example, E bar 0 is essentially the universe, and in particular then maps from X into, or so this is like externalizing it, so this gives you like this, up to small objects. In particular, if you plug in the terminal object, you get exactly the small object. Cool. So I have a notion of, so let me come back to my list of conjectures here. I have a notion of infinity category that I can define, and I can internalize it. I can internalize my category. Cool. That's a good first start. Can I go further? So can I actually prove that this internal infinity category now is co-complete in particular provision of the point? And do I have 15 minutes or 1 hour? I should have asked this before. Do I have 15 minutes or 1 hour? 1 hour. Cool, perfect. Thanks. All right, good. Okay, so what remains is then is E bar co-complete. Right. So before I actually try to say anything serious about this, well, let me like cover a kind of like a special case of this, namely the counter co-complete case. So let me make a small detour. In the co-complete case. So let me add the assumption. Let us also assume that E has geometric realization. So meaning there is a colimit functor from this like this. All right, that makes sense. Then my claim is we can actually do what we want. So then the theorem, and here you have to be okay, like I should say if. So let me like be a little bit precise about references. So this theorem, this is out, but not exactly stated as such. I've slightly rephrased the story, but there's a paper univalence in higher categories, and this is there stated as a theorem. This is like more recent, so it's not out. So like it's like I have written like a draft, but like not out yet. So I'm still checking some things. But it should work as described. All right. So it's the statement now. Now with C, with E, the category as before, but with the additional geometric realization. The claim that we have is that now, so if C is, if E is as above, then E bar is the co-completion of the point. All right, so I have time, so I can give you actually a proof sketch here. And so the proof sketch is essentially using ideas of like two other people in a like a effective manner. So concretely, there's like the work of Louis Martini, who was a PhD student of Rune Haugseng, and Sebastian Wall, who was a PhD student of Denis Charles-Sosinski. And so especially Martini, but then later in collaboration with Wolf, essentially what they have done is they started with like a presentable infinity tuples, so infinity was in the sense of Louis. And then they define exactly, they take the standard definition of internal infinity category, like this, so like the common single object. And then they essentially redevelop all of like category theory in that setting, up to and including what it means for this internal infinity category to be appreciated, presentable, even a tuples. Right? So internal true and infinity tuples, but with the presentability assumption. So on the one side, it's super cool and nice, right? So it's a direct generalization of everything that existed. On the other hand, it doesn't completely work for what we want, right? Because it's like you cannot just always externalize everything if you have something. Yes, there's sometimes a mismatch. But yeah, so the idea is to like realize that there was one thing that was like you needed where they use presentability, but I happen to have already done it before, so just work like that. Kind of like a coincidence. So the kind of steps of the proof to get you a sense is to like observe so first of all, C bar, I don't know why I switched E bar has a terminal object. And so we get a kind of like a vibration here. And this is a so-called, what people call a universal left vibration. And by which I mean that, okay, now E bar, I can take a look at maps from some other internal infinity category like C bar into E bar. And the claim is that this is equivalent to some kind of vibrations over C, which I have not defined. So I'm just claiming there's a notion of vibration internal to simplicial objects in E. And I can exactly characterize this. This is a kind of like, maybe if you want like some kind of directed movement. But I would just think of it as like an internal spectrum, because I'm more of a category. So depending on which perspective you take on this. And why is that beneficial? Because now if I have this result, I can kind of stitch together several maps to get my desired kind of colimit. Namely, I can take, so I can go from, maybe I should use fun here. These are like, yeah. So internal functors. Right. So I can take this to my left vibrations, but then left vibrations are just special cases of simplicial objects. So but then I can just post-compose and go to the base case. And here, all I need left is the geometric realization. Because I have simplicial objects now in E, and so I just take the geometric realization. So I get this. And the claim is that this internal functor is my column. Because more or less everything is like, the key thing is that this is universal. So it all fits together. I see some head noddings from the kind of people who like vibrations. So good. That's a good sign. All right. And so now, okay, this just proves the colimit. You also want to show that it's universal. For that, you kind of like a relative version of this, which is like slightly more tricky to explain. So I will skip that. But you like do the same thing, but instead of like doing it over diagram, you do the diagram over something, and then you get like similar result. So yeah, this is like a sketch of the argument. And the place where the representability in the original argument is basically this equivalence. So in this equivalence, that they internalize the straightening by using the external straightening that is already known from Fleury and other people. But I think you can just get away with it like directly, because you can kind of construct E bar directly without this. All right. So we could say, coming back to our conjecture here, good if we assume geometric realization. All right. Okay, so let me then come back to the general case. Back to the road. And here the key observation is that having the geometric realization is like actually not just sufficient, it's actually necessary to get exactly make this kind of argument. Because I mean, you cannot get around it. If you have colimits, you will need geometric realization in particular here as a step, because it's in something like just a Googleification of like some kind of arbitrary infinity category. So there's no way to avoid it completely. So having geometric realization is actually necessary. This means that in our assumptions, if we can find an example of something that doesn't have geometric realization, we cannot generalize this theorem. Like we can have the internal infinity category, but we cannot prove its Coulomb. All right, this is what the statement means. So let me give you an example of this. Take my favorite example of a non-presentable tuple. And it's let's see. We still have okay, I have time. So I can actually explain this. So I take the category, take the, so I will give the name, but I will explain what it is for the people who already know. So take the filter quotient, infinity topos with the Faget filter on N. Okay. So if you don't know what that means, let me actually explain. It just means, okay, I take the there's various ways of doing this. Let me give like a very explicit description of this, more or less. It's a category with, which we denote like this. It has objects, just n tuples, where n, where xn is a space. So let's say a topological space to be more explicit. Okay. And the morphism is just given by chains of morphisms. Like this, collections of this, for n bigger than a certain n. So I pick an n and start out morphisms, but then with an equivalence relation up to what they call eventual equality. So two morphisms are identified if they're eventually the same. Eventually means from some number. So this infinity category has a nice functor from just taking the naive product and inherits a lot of properties from it. So this functor preserves a lot of cool things, such as like finite products or finite limits and colimits. Finite universes, so object classifier, local Cartesian closure, like whatever finite property you can think of, it will probably fine. But as soon as something gets infinite, then it doesn't. Right. So does not preserve presentability or even countable coordinates. All right. So this was known in the elementary turbos case for a while, like maybe 70s or 80s. Like Johnson was thought about this, Adelman also. For the infinity case, I thought about this for a while, and it was clear that this category doesn't have co-products. But I think you can make a similar argument to deduce that it also doesn't have geometric realization in the naive sense. So let me try to make a case for this. And that's like a fun example. So take the functor from delta up to this category here, which takes n to the n-fold product of S0. Very simple. And all the boundary maps, the James maps give my projection and so on. Then the colimit of this diagram, let me give it a name, S0 dot. The colimit of S0 dot can be given as the sequential colimit. So this is over delta up. The sequential colimit where I like truncate along the way. All right. Now these ones I can actually compute, right? Because these are not finite colimits. And I said finite colimits just transfer. So easy. But 0 is just the point, so this is just S0. This is the join of S0 itself, just S1, S2, S1. And so the claim is that this doesn't have a colimit. And now this is the sequential colimit, so looks easier, I think. And so here the technical claim I will make is that while I'm technically was working in some kind of infinity category setting, but everything that I said, this thing comes to the model structure. The simplicial model structure that is not covalently generated. So it doesn't matter, but it's a model structure. And so I can look at this is a nice projectively cofibrant diagram in this model structure. So I can just try to see, I can reduce it to looking at strict colimits. And so now can we see why this doesn't have a strict colimit? If you have worked with further quotients, then I think it's not that bad anymore. There's various ways of seeing it. Let me tell you one, maybe that you find more or less convincing. So yeah, now notice there's a nice adjunction between like now top, literally the category top strict to the category set. All right, so this is like disk and this core disk. So the usual adjunction transfers here. So all I can just, in order to like look, this doesn't have a colimit, I can just take the underlying thing and look at the colimit there. And there I don't know, I know it doesn't exist, right? Because the colimit of USN, I can reformulate this as like the core product of like something like this. That doesn't exist. We don't have infinite core products. It's very standard. If you don't like this argument, you can kind of reverse engineer why this doesn't exist into the setting of top itself and make a great argument. It's not too bad. All right, cool. Or not cool. Yeah. Any questions about the last two proofs / sketches? I have no idea if I went too fast or too slow. It's hard to make it out. Yes.
One thing I was confused about, you said you had to do eventual realization on the external level.
Yeah.
And then in the proof you used it on the internal level. Step. You start by having the correlate from each delta E, and then you prove.
So why okay, what's happening is that how do you define a map? I want a map from the universe in simplicial objects to the internal infinity, so the internal infinity. Those are both simplicial objects. Okay. So what I want is a map from here to here. And how do I do this? I do it representatively. And then, okay, you unwind the definitions, and this is exactly simplicial objects over X into just objects over X. That is the geometry. If you want it to be universal, if you want it to have the right property internally, you need it to be a geometry. Okay? Other question. That was very question, please. I cannot skip that. Cool. So I know one person is following. So my plan is working. All right. So where does this leave us? What comes out of this? Like what just happened? Why is it like, I mean, I give kind of like a technical mathematical argument why this diagram doesn't have a column. But if you like went to, I don't know, a slightly advanced algebraic topology student and showed them this diagram, so you say the spheres and embed them in each other, what would you expect the column to be? Very naively, you'd expect the column to be something like S infinity, i.e. contractible. So why did that not happen here? Like what occurred that prevented it from being this desired colimit? In some sense, the problem is that there are too many numbers in this topology. right? So something that's kind of hidden in this argument is that this topos has a natural number object, but this natural number object has way more natural numbers than just the standard ones. And so I'm not indexing over, and so in particular for every natural number I get a sphere. I'm not indexing over all spheres here. I'm just indexing over the standard ones. So I'm not getting enough connectivity. Like the connectivity doesn't rise to the level it should. What I should do is index it internally by all natural numbers that exist, and then the internal complement would exactly be compact. That's what I would expect from this. But the problem is there's no way to fix this because my choice of delta was built into it the second I chose my notion of internal infinity category. So, so what this leaves us is that everything I said is basically wrong, right? More or less. So, it leaves us in a tricky place. And like notice, just before I continue, so in this exact assumption here, I kind of could get around this here. So by kind of assuming enough co-limits, I get some control over the natural numbers. But if I assume like no co-limits at all, then I kind of lose all this. This is kind of like there's an interplay between how co-limits in the infinite co-limits act and what kind of natural numbers they are. So ideally, what I need to do now is to rework all of infinity category theory, but like one step further internally. Like we were not internal enough. And so here's, I think, a nice kind of interplay between category theory and type theory that I would like to make. So the benefit of category theory is that because there's an external layer, sometimes some constructions get easier compared to type theory, where like everything has to be like super internal. The drawback of this is that sometimes you're not internal enough. You always run the danger of like making a construction and not realizing that you are actually at the level you should be. So yeah, what we want to do is then redefine everything, and I'm not going to do this anymore because I only have 4 minutes. But this is anyway like future work that I want to work on is to what we should do is define internally now some kind of the category of simplices in E as E infinity category, which one can do in a variety of ways because this is actually one category. It's actually univalent on the nodes, right? It has no automotive. Super nice internal category. And then define, and I have no good name for it yet because there's already this notion. So like, let's just bake it and call it a truly internal infinity category, E infinity category as like a simplicial object now here. So now those are internal infinity categories. I'm defining a functor as a truly internal infinity category that satisfies the right conditions. And when I say right conditions, so the completeness condition is univalence is basically the same. It doesn't change too much because it just depends on up to level 3 and at 0, 1, 3, nothing changes. The Siegel condition has to be adjusted, so you kind of have to make it more inductive, but that's also not too hard. So instead of just using standard description, you slightly change it. So you can define it; it's not too bad. But the problem is like there's very little category theory in the classical, because nobody in the more classical category theory literature has worked on this. So a bunch of stuff has to be redeveloped if you actually want to get this problem. So yeah, I don't know. It's like as they say, hindsight is 20/20. Like maybe this was clear for all of you from the beginning, but like it turned out it was not as clear to me. So like at least for some cases it works very well. It's like a nice story. But for the one case I really wanted to, it doesn't give me the result I wanted. So I will end this talk then with the realization that where is it? That I guess there exists a notion of internal infinity category, but there is not even an internal category for it. I don't know how to lift it, and I also don't know how to construct this. So kind of did this whole story and I came back to like not knowing much. Okay. And with that, I thank you for your time. And if you have questions, please ask.
Thanks for that talk. So, second.
If you come back to the energy talk, I was wondering whether you could construct this delta E as a sequential coordinate of the finite pieces that you would construct those finite pieces in an inductive way from something very on the properties you expect the external reflection, the external reflection of the simulation whatever simplex you have.
You mean this object?
Yes.
So this is a simplicial object in E.
Yeah.
So it's sequential colimit would be a sequential colimit in E. I'm not
Yes.
assuming E has sequential colimit. That's the I think the problem is that.
Okay.
I think if I assume it, then probably if I assume sequential colimits, then I think everything reverses to the standard case anyway. Right? If I have sequential countable colimits and I have finite coproducts, I have infinite coproducts. If I have infinite coproducts, my national norm is standard. And then I have more. Then we are back to this case and everything is good. That's like the problem. Exactly this.
Okay. Perhaps this precise sequential could exist but not the relation level, but it's very interesting.
I guess. Yeah. Yeah, we could. Yeah, I don't know.
Thank you.
Then let's see the definition of infinity category. I think somehow I cannot use in fact. And I mean, the reason is somehow because of two jealousies, because data is not direct. And I think the deeper reason is that there's something fundamentally wrong about this kind of definition, because we have a weak definition of composition, but the strict definition given by the index category of identities, of degeneracies. And in some sense, both of them are degeneracies are like empty compositions. Both should be weak. And I mean, you can do this. You can do this direct replacement of delta and get a constructively reasonable definition of infinity. Maybe that would address your problem with the other.
Yeah, definitely. I cannot agree or disagree right now because I've not thought about it too much yet. But yeah, it could definitely be possible. Like, I mean, this is like, I mean, just a suggestion. It could definitely be possible that one would like to replace delta with either like a fattening of delta. Maybe you want to replace delta with cubes. You want to internalize that something like this. There's a lot of the range of possibilities that we'll consider. My only realization is kind of that the stochastic thing doesn't work. It's just not deep enough. What the correct answer, I'm not sure. I'm happy to pursue various options.
Any more questions? So let's participate again.